And greetings everyone, welcome to the Evidence Reasons Academy. This is probably going to be a heavy day for streaming. It's awfully hot outside. I don't feel like working outside to do the gardening. In fact, I've been working at night with lots of lights outside to do kind of improve the curb appeal of the house. And it's so hot, it's hard to even work inside. So I'm just going to do kind of nerd stuff today. Kind of get it off my chest. I also have a debate November 10th with an evolutionary biologist, J.F. Garapi. Forgive me if I mispronounced his name. And yeah, there's a saying in World War II: if you're over the if you're taking a lot of flack, you know you're over the target. I've been taking a lot of flack lately. I mean, not just from random YouTube riffraff, but I know university professors are watching what I'm saying from all around the world. And there's a saying that it's better to be criticized than ignored. And part of my approach is that I will just try to use what is inside peer-reviewed literature textbook and try to stick to that. And evolutionary theory is falling based on that. I'd like to explain why I believe in the ether. This was not fashionable when I was going through graduate school, but you know, if you keep your pulse on the latest research, you'll start to see where cracks are being, fissures are starting to break in kind of sacred cow theories like the Big Bang, and sometimes even in the textbooks. And it's in the textbooks if you're willing to kind of just view it. In my in my book on general relativity by Bernard Schultz, it talks about where relativity will fail. And I wish I had the page number, but I don't really need to reference it now because it seems common knowledge when a mathematical physicist who's well known, Sabine Hossenfelder, said Einstein's relativity, general relativity, which includes special relativity, can't be quite right. Einstein's relativity can't be quite right because of quantum mechanics. So most physicists will say, which would take precedence, quantum mechanics or anything else? Really, quantum mechanics takes precedence over everything. So you'll hear the mention of like classical viewpoints like classical mechanics, Newtonian mechanics, classical electromagnetics, which is Maxwell's equations, and then general relativity, which is actually considered now a classical theory. Maybe before that was groundbreaking because it seemed at variance with Newtonianism, but now it's considered classical. All right? So there's a time it was considered earth-breaking, shattering, modern. Now Sabine Hossenfelder and others call it now a classical theory, because quantum mechanics is now considered to take precedence. And for that reason, she said relativity cannot be quite right. And so everyone has their opinion on how to correct this, because we certainly have experimental evidence that relativity may not be quite right. It's mostly right. And so how do we reconcile this? And I would say, as I've looked at this and going back to some of the old math and even some of Einstein's words, try to tease this apart. That's one reason I spent a lot of time going through this derivation here, which let me just show it. this derivation here. So there is the Lorentz transformation factor right there, the Lorentz factor. Einstein and Lorentz. The Lorentz factor is at the heart of special relativity, the Einsteinian version. But there's also the Lorentzian. So this transformation factor happily sits both in the Einsteinian version of special relativity as well as the Lorentzian. This is a nerd dumpster fire. That's meaning that I'm going to be exploring some, I'll be reading through a lot of stuff and fumbling through it. It may be slow, it may be tedious, may not be fun. This is more, when I say nerd dumpster fire, that means it's going to be like a reality TV show. What you see is what you get. It's not immediately designed to entertain. You'll actually see me stumble through derivations and reading things and getting stuck. So if you just want to see what the life of a professional creationist is like, this is going to be a taste of it. It's, it's nothing spectacular. That's why I say it's a nerd dumpster fire. If you may be totally bored to tears as you watch this, as I kind of fumble through textbooks. So that's what you're going to get. So, as I said, this was the derivation that I take that has meant a lot to me. I worked on it for 6 weeks. It recapitulates what is well known, well established in physics. I wouldn't say it's well known, but this is the derivation I had to work through. I kind of like my version of this derivation because I think it's prettier with all the nice colors, and it is very rigorous. You can see all the steps, and this connects electromagnetic theory to special relativity. And I had been referencing this textbook by Griffiths on engineering, electromagnetics. My opinion has declined on this book. This book is a much better book on electromagnetic theory. And there you could see the two equations, operators on Maxwell's, parts of Maxwell's equations, the curl of E and the curl of B. It turns out you've actually seen that in the derivation that I was making. And this book has, just look at the cover, just tons of that. And this is not easy reading. You can't just look at these equations and just like, oh, that's easy to understand. The meaning takes days to kind of uncoil. It's very sacred. You have to kind of savor what's there. And so Maxwell's equations. But I point you to this chapter, Electrodynamics and Relativity. Electrodynamics and Relativity. Isn't that awesome? And that's the last chapter. Let me make sure. Yep, that's the last chapter in this book. It's connecting Maxwell's equations to special relativity. And there are a number of ways to do it. I kind of like the way that I did it. Just brute math. And I showed it again. I love showing this off because this is kind of a personal victory that I learned how to do this again. I had to do this in grad school, but now I'm able to do it again and actually understand what I'm doing. The professor kind of spoon-fed us with lots of hints and training wheels and handicap. This is where I had to do it actually from the ground up, almost totally on my own. Thanks, hat tip to Dr. Bersha, whose video kind of gave me a couple critical parts, and I had to work through this. So again, it's fashionable now, mainstream, to say relativity can't be quite right because of quantum mechanics. So I'm not. And then let me show you a Wikipedia entry. Let me show a Wikipedia entry on Let's look at this, 0-point energy. Let me show this, 0-point energy. The 0-point energy is the lowest possible energy that a quantum mechanical system may have. Unlike classical mechanics, quantum systems constantly fluctuate in their lowest energy state, as described by the Heisenberg uncertainty principle. These fluctuating 0-point fields, and I'm just going to go here, these fluctuating 0-point fields lead to a kind of reintroduction of an ether in physics, since some systems can detect the existence of this energy. However, this ether cannot be thought of as a physical medium if it is to be Lorentz invariant, such that there's no contradiction with Einstein's theory of relativity, special relativity. Okay, that last sentence I utterly disagree with. It is I will utterly disagree with it for a certain reason. And Jamie Russell, greetings, Jamie Russell. Let me just let me give you my greetings here. Welcome to this dumpster fire, Jamie Russell. And I'll say, is there a universal time? Yes, according to quantum mechanics. No, according to general relativity. Yes, according physicists, because quantum mechanics takes precedence. Okay, there you go. And greetings. Okay, so just going back here. So there are two statements here. One I agree with, one I utterly disagree with. These fluctuating 0-point fields lead to a kind of reintroduction of the ether in physics, since some systems can detect the existence of this energy. The sentence I disagree with, the ether cannot be thought as a physical medium if it is to be Lorentz invariant. That's not true. And that is what I'm going to try. Why do I say that? Lorentz was the one who believed in the ether, wrote his Lorentz transformation that tried to create the invariance in an ether medium. And I'm going to show that it makes more sense that there is Lorentz invariance with an ether medium. In fact, you can't run away from it. Can't run away from it. So honestly, if quantum mechanics takes precedence with an absolute clock and general relativity can't be quite right, which means it's mostly right but can't be quite right, we have to figure out how to reconcile experimental observations and then also invoke an absolute clock, an absolute time. And since Jamie Russell brought up the topic, I'll mention it here. Time problem. Just look up this Wikipedia entry on the time problem. The problem of time. In theoretical physics, the problem of time is a conceptual conflict between general relativity and quantum mechanics. In that quantum mechanics regards the flow of time as universal and absolute, whereas general relativity regards the flow of time as malleable and relative. The problem raises the question of what time really is in the physical sense and whether it is truly a real distinct phenomenon. It also involves a related question why time seems to flow in a single direction, despite the fact that no known physical laws at the microscopic level seem to require a single direction. For macroscopic systems, the directionality of time is linked to first principles such as the second law of thermodynamics. So I worked through these equations, and so you can't say that I haven't tried to start with first principles of like classical electromagnetics, and we'll cover some more experiments because that's where it's really going to count. We have classical electrodynamics, and that's represented by this D'Alembert. You could take Maxwell's equations and formulate a D'Alembert, which is the wave equation. When you apply the Lorentz transformation and do some calculus manipulations with chain rule second order derivatives, you're able to show the connection between electromagnetism and relativity. And I was pointing out that what was amazing is the Michelson-Morley experiments in 1887 combined with they were using oil lamps. They didn't use electric light bulbs because electric light bulbs hadn't really been in prominence. It might have been invented right around that time, and it wasn't available to them. They were using oil lamps and this interferometer with a little telescopes mounted, and they're looking at these halves. It was an incredible setup. They put this thing on a mercury bath and was rotating it and just making observations. This is just unbelievably. This is incredible that they were able to do that. When they did this, the results from their observation of an oil lamp combined with this equation here that I'm showing off, equations like this, that Lorentz derived. This isn't my derivation. This is Lorentz and others. That the faster you go, they are able to show that the faster you go, based on that oil lamp experiment. This is what I call real science, and why I think evolutionary theory doesn't even compare, because they took the experiment of an oil lamp and deduced from that, if you're in a spaceship and you go faster, close to the speed of light, then a day for the person on the spaceship would be like 1,000 years for the person that's left on Earth. So, in fact, I think I want to add the Michelson-Morley. Let me see, Michelson-Morley. Interferometer. This is just beautiful. There it is, right there. That's the Michelson-Morley interferometer. And there's an oil lamp. I presume it's right here. They had all these mirrors and stuff, and this is the apparatus. They put it in the basement here below. So it's rotating. It's sitting on a mercury bath, which is really dangerous for your health. And they were looking through these telescopes here, making observations as this thing slowly rotated. And this is just incredible that they did this. They put it on a mercury bath to help isolate vibrations. This is just insane. And this is a stone slab sitting on a mercury bath, oil lamp here. And so now let me insert this picture into my document. Because this is landmark. This won the Nobel Prize. And they said this is the greatest failed experiment in history because Michelson was trying to detect the ether. There are arguments now that his first interferometer that was done with air actually detected the ether. The later ones that were done in a vacuum were not able to, and that's going to be a real sticking point when we talk about future experiments. This is what I call real science. You could take an oil lamp and predict how spaceships would behave hundreds of years, over 100 years later. Phenomenal. Evolutionary theory doesn't have predictions like that. People are like, you're a creationist, you hate evolutionary theory because you're a creationist. Well, that's partly true, but I also, because I've seen real science. And evolutionary theory is not real science. This is an example of real science. So let's go back to this where I was. So I'm trying to point out special relativity did invoke the ether. The first version that had all the time dilations was Hendrik Lorentz, he was very pro-ether. So was Michelson, Morley. The guys who made this were pro-ether, and to their dying days, they kept searching for evidence of it. There were a lot of people that were still sympathetic to it, and I think especially now we have a friendlier climate in light of quantum mechanics that there has to be an ether. I pointed to the zero-point energy, and they're saying, you can't maintain Lorentz invariance. I'm going to contest that today. If you have a traditional medium, I'm going to explain why. At least I'll do my best. But let's see. I mean, if you have a zero-point energy and you have all these things moving around, there's going to be a mean velocity where the mean velocity is 0. So technically, there's going to be a stationary absolute rest frame. So let's talk about what Einstein. I mean, let's show what current textbooks say, and it always bothered me. No absolute rest frame. No ab. Let me just show what I'm typing here so you could see it. So let's say no absolute rest frame. Relativity. So all right, so you go here, physics form, no absolute rest frame. And from the official NASA website, the following material, okay, this is from an official NASA government website, but there's a disclaimer. The following material is being kept online for archival purposes, although accurate at the time of the publication is no longer being updated. The page may contain broken links or outdated information, and parts may not function in the current web browsers. All right, given those caveats, no absolute rest. Okay, so here it is. There exists no way to tell which of them is moving and which one is at rest. Okay. Okay, so according by Newton's laws, two frames of reference moving with constant velocity relative to each other observe exactly the same physical behavior. There's no way to tell which of them is moving and which one is rest. There's no absolute rest frame and no absolute constant velocity. Okay, this is Newtonian. All right, so the Newtonian view is there's no absolute rest frame and no absolute constant velocity. That's actually the Newtonian view. In the 19th century, the laws of electricity and magnetism were discovered, suggesting that light itself was a related phenomenon. An electromagnetic wave is further discussed in the sections about the sun. But for a while it seemed that by certain subtle effects, electromagnetic forces could distinguish between whether a frame was in motion or not. But for a while, it seemed that by certain subtle effects, electromagnetic forces could distinguish whether a frame was in motion or not. Those effects were hard to verify, and when they were finally tried out, they did not work. They could not tell which system was in motion. I'm going to argue that's false. I'm going to argue that's false. You have to be more subtle than... I'll argue it's false, not because the Michelson-Morley experiment refuted it. You have to go a couple levels deeper where you involve acceleration. Michelson-Morley was not dealing with acceleration, it was dealing with velocity. When you take a measurement over time, where you involve acceleration over time, you'll start to see this effect. You get experimental stuff. It's going to be undeniable, in my opinion. So let's see. Let's just continue here, because I'm trying to state what the mainstream theory is. Albert Einstein proposed in 1905 the principle of relativity as a fundamental property of the universe. No matter what physical process was used, absolute motion at a constant velocity was undetectable. No loophole existed, not even through the laws of electricity and magnetism. This is one of the best explanations of mainstream theory. I'm not saying I agree with it, but it's one of the best explanations of mainstream theory that I've seen. That actually, I mean, because people have said Maxwell was a Newtonian. I'm just like, well, it depends on what you mean by he was a Newtonian. Because if you believe in an ether, then in some respects you're not a Newtonian. I mean, are you or are you not? It doesn't matter. Is there absolute motion or not? Let's not do what philosophers do and make such ambiguously defined terms and conflations, and you just get these endless arguments, and hence you perpetuate a field. You never get anything resolved. Sorry to be on my soapbox about philosophy. But I like this. Oh my goodness, I'm gonna bookmark it. That is, oh my goodness, this is one of the best explanations. That Newtonian is actually a very relative, there's Newtonian relativity where there's no absolute motion, and Einstein supposedly confirmed that, and then Michelson-Morley supposedly confirmed that. But Michelson-Morley was distinguishing between velocities, and there's subtle effects that we get with the Lorentz transformation, and just to show people that I actually did my due diligence. Just to show people I did my due diligence. I started with the electromagnetic wave equation, the d'Alembert here. So, which goes back to, I should even put in Maxwell's equations. So let me start with Maxwell's equations. I'm going to insert it in this document. I think I owe it to the document to have this, to make a good document. Let me just... So if we start with Maxwell's equations, so let me include that, Maxwell's equations. Maxwell's equations. And what's my favorite version of this? So if we start with, that's so tiny. See, can I get a bigger one? That looks a little bigger. Let's see if that's bigger. Better. The Maxwell-Faraday law, that's the Ampere circuital law. So what came first, the Michelson-Morley or Maxwell? It was Maxwell. So we start off with Maxwell's equations. And you could see, I should now be able to name that. This one is Faraday's law of induction, at least the left-hand side of the equation, and this is the left-hand side of the equation of the Ampere-Maxwell law. Ampere's circuital law with Maxwell's correction, so it's called. And you see it right here, right there. This one right here and this one right there. Now let's see what else I need to say. The beginning of all this, the experiments that made this is just incredible. So let me see. I need to give credit to Michael Faraday. He deserves. Faraday. equipment. I mean, this is unbelievable what his original let's see, let's look at oh my goodness, some of the equipment he built is, I mean, by today's standards, your jaw would drop. Yeah, this is one of his devices. I mean, it's just unbelievable that he could start with something like that. I mean, my jaw just drops. Faraday inductor. This is like 17. When was this? This was 18. This was a magnet built in 1845 for Faraday to use in his experiments. 1845. So where some of this came from, okay, this is 1845 experiment. This is just beautiful. We have an 1845 experiment. I mean, God bless these electrical engineers. Huh? Let's see. The pioneers of electrical engineering. Oh, I didn't mean to do that. Sorry, guys. Let me recapture that picture. This is just beautiful. And let me see. Maybe I put it in the wrong bin here. I think it downloaded where I didn't want it to go. Okay. Let me look in my... See if it went to my downloads place. Downloads. Nope, that's the Michelson-Morley interferometer. Let me try to download this again. Apologies to the viewers. So we'll go here. We'll go... I'll save the image. I'm going to put it... No, it won't let me save it as an image. I want to save it as JPEG. I know what, I'll use my hang on. Oops, sorry, I killed my... Didn't want to do that. One moment. This going. I'm gonna get that. I'm gonna get that little guy. So new. Faraday inductor 1845. Let me do a little cleanup here. That's the Faraday inductor 1845. Darn it. Why can't I finish editing this? My system's slowing down. Oh, I know I'm hitting the wrong button. 1 second. Oh boy. $18.45. Okay, so now I'm going to insert this into my document. So we had devices like this that we started off with. And then this led to Maxwell's equation. You could see it here, the Maxwell-Faraday equation. So Faraday was spending time, can you imagine just using iron and then wires wrapped around, and Faraday's just working on that. They developed this law, which is critical. Then Maxwell found this other law here. And Ampere gets credit for that, and I don't, Faraday's a better known name. I don't know exactly all the reasons why, but Maxwell was able to figure out this equation here. And then from that, we combined with the Michelson-Morley experiment, we were now able to make judgments about space travel. This is just unreal. It's just unreal. Oh yeah, Jamie, he said you can ignore my comments. I am just thinking out loud. Thanks, Jamie, because this is a big workload on me to try to actually work through this. All right, so now we have this Lorentz transformation that relates what will happen in the spacecraft. So let me back up a bit. So we had Faraday with this experiment, and then a number of other things contributed. So Faraday contributed to this formulation here. There are other people that were involved. Some of it just pure mathematics like Gauss and then Ampere. So I'm not showing all those experiments. So you combine this plus this. You start off with this. That led to that, and other experiments led to Maxwell's equations. Maxwell's equations then combined with the Michelson-Morley experiment led Lorentz, who is pictured here with Einstein, to figure out the behavior of clocks. And so Maxwell's equations, led to this. This is the D'Alembertian, and then Lorentz, starting with the D'Alembertian, created this system of equations to reconcile the Michelson-Morley experiment with an ether and Maxwell's equations. This transformation here then led to the way clocks behave. So now let me see if I can make a PowerPoint to describe what the issues are. So I'm going to start a PowerPoint, and let's see if I can do a blank presentation. And I'm going to insert new blank slide. Okay, so there is the integral velocity. All right, unfortunately there's funny things when you have clocks, but let's say we, from the observation of like where a spacecraft takes off, let me try to do this. So we have to figure out what whose clock will be used as a reference for observations. And you can use multiple clocks, different observers. Acceleration. It's the integral. You'll see an integral here. I wish they didn't make this so hard. And I'll use integral. I could type it myself, but that's going to be painful. Can't we just get a simple formula here? There. I like this one the most, but why did they add all this other stuff? Integral. Let's see, velocity integral. Let's try this, velocity integral of acceleration. See if I get a better one. Come on. I'm going to go with this. So I'm just going to post this in the as a starting point. Oh, wrong. Insert pictures. We don't need all of this here. So let me just kind of strike that temporarily. See if I can blank it out. Sorry, try again. Insert, and I want some shapes. This. Good. And so I'm going to change the shape fill white. Nope, I want shape fill white and outline. No outline. See, that's better. So we start here. Velocity is the integral over time of acceleration. But you know, guys, you kind of like in kind of just from human experience, when you're riding a jet airplane, when it's on the runway, you know, and the pilot guns the throttle to try to take off, you're pushed back in your seat and you can see yourself accelerating. You could feel it too. You feel the G-forces. And that takes, over time, you just get faster and faster as long as you're feeling that acceleration. Okay, so that's very, very basic. So we could say then, if you had a cesium beam atomic clock, it's actually a big thing. We actually did this. There's a Heffel-Keating experiment here. Let me see if I could show it. We actually tried to do this. Unfortunately, their math got complicated because of the nature of the experiment. Heffel. So what they did, there's this Heffel-Keating experiment, and this is one of my favorite pictures here. Oh, look, there's the flight attendant. Oh. Heffel-Keating. So, hang on, I'm sorry, I should have shown what I'm doing here. There's the Heffel-Keating experiment. And I'll put it in the PowerPoint. So I was describing we had an airplane, and you're feeling acceleration, and what they did is they took a cesium beam atomic clock, the world's probably one of the world's most reliable clocks, the cesium beam atomic clock. And I wish they had a better picture than this. So you could see the two atomic clocks here. They put it on board an airplane, and they flew the airplane around. And then they had, the Naval Observatory had, I think at the time, 6 atomic clocks. They were able to persuade the Naval Research Lab and Observatory, whichever, to loan them these atomic clocks. So they put 2 atomic clocks here, and they flew it in an airplane. So when you're, as I said, when you're in an airplane, you feel the acceleration, you're getting faster. So according to the Lorentz transformation, you should start to experience, your clock should slow down. According to the Lorentz transformation, this is the prediction of all these. That's the prediction of this equation I re-derived. Again, I'm emphasizing this is not original to me. This is me just recapitulating my graduate school work. Oh, this took me weeks. So let me show you. So I re-derived this equation here. This confirmed the Lorentz transformation that the clocks would slow down as pictured here. So you're feeling acceleration, and the clocks slow down, and they bring it to Earth. They're supposed to with some corrections for gravitational fields, they were able to confirm this equation experimentally, the consequences of this equation experimentally. And I spent 12 hours trying to describe what this was, but the bottom line is it worked. Now that's a gross simplification of things because that experiment had to actually deal with special, also general relativity effects with the Earth's gravitational fields. Okay, so, but they confirmed that the clocks were affected within theory predicted by special relativity and as well as general relativity. So this is just one component of the clock adjustment that they, the change in the clocks that they detected. Wikipedia goes, you can just Google it and you could see all the numbers and how it was a very successful experiment. And the more important thing is our GPS clocks also experience this because the satellites are moving very fast. They're also farther up in the gravitational field. They have to make very subtle adjustments to their clocks so we can get more accurate position data. Your GPSs are more accurate because we account for these special relativity effects. That being said, oh, thank you, Dan Straight. Let me just say hi to you, Dan Straight. God bless Dan Straight. I'm just going to give greetings. So, where was I? The GPS system now works because of something called the Hatch filter. Hatch was a physicist. He was not an Einsteinian. He's a neo-Lorentzian. So we believe in the varieties of what we call relativity theory. I prefer to call it invariance or absolute theory. Absolute theory with the appearance of relativity. So if you want my position, there are absolutes in the universe, not just in terms of moral laws and God, but absolutes in terms of position and velocity. And there's only the appearance of relativity. So I'm more of an absolutist, but we still call ourselves neo-Lorentzian relativists. Okay, don't worry about the mincing the words and the semantics. The math will bear out what we mean. But Ron Hatch, our GPS works because Ron Hatch's filter is in there. And he was not an Einsteinian relativist. He's a neo-Lorentzian relativist like me, which means in a way we're absolutists, okay? So, and that's a long story. You'll sort of get that from here. So again, we had the Heffel-Keating experiment where you're on an airplane, you experience acceleration, you're moving faster, and as you move faster, the tick rate on the clock is slower. How do we know it's slower? When he lands, we compare this clock to the one that was on the ground, and we see the difference, and it accords in a small way with this twin paradox. Hang on, it accords in a small way. I'm sorry. So we had the Heffel-Keating experiment. We confirmed that the clocks in the airplane, after the airplane landed from its numerous trips, they brought the clocks to the Naval Observatory where we had the quote-unquote stationary clock. Granted, it's not really stationary because the Earth is spinning and also rotating around the sun, etc. But we brought these clocks back, and what did we find? The clocks had slowed down in accordance with theory. And so in that Bible verse that says, one day is as 1,000 years and 1,000 years is as a day, if that airplane had been able to move very close to the speed of light, if we just extrapolate that, then like in this hypothetical picture, the girl flying at 99.999999996% the speed of light, a day for her would be like 1,000 years for us on Earth. So the math predicted, accurately predicted, the math is a triumph, the math accurately predicted, based on prior experimental results, it accurately predicted future experimental results long after Lorentz had made these predictions that the clocks would be affected. And it was affected according to his calculations. So this is a triumph. This is why I like physics. People can make predictions with math and the experiments in their present day, and then hundreds of, maybe 100 years later, it's confirmed with experiments with our spacecraft. That's real science. Evolutionary biology doesn't have that. I could point to so many failures. It's hilarious. Sorry to pick on evolutionary theory, but people wonder why I'm so negative on it. Not only it's because I'm now a creationist, but I compare stuff like this with evolutionary theory. There's just like no comparison. In science's pecking order, evolutionary biology lurks somewhere near the bottom, far closer to the pseudoscience of phrenology than the physics. That wasn't a creationist saying that. That was Jerry Coyne, who wrote the book Why Evolution is True, which is kind of funny, the irony of it all. Anyway, Dan Straight said, biology is science, evolution is religion. That's right. It wasn't a creationist who said that. It was Michael Roos, who's an evolutionist. He said Darwinism is religion. It's funny. That's the one benefit of having wasted so many years studying evolutionary biology. You get all these juicy things in a moment of, in a moment of, just being blunt and honest and self-reflective, they say stuff like that. Okay, so now let's get back to where we were. So now this raises the question, and see if I could draw this. All right, so, and this was actually subtly put in the Hafel-Keating experiment. They actually had, let me see if I could maybe draw this and see if I could get an airplane icon. Okay, airplane. I'm just going to grab a picture of an airplane here. I kind of like, name a favorite airplane. I like the, what's a nice, the X-15. No, how about the Valkyrie? XB-70. I love that airplane. So let me see. Come on, give me a nicer picture of the Valkyrie. Da, 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 da. Okay, let's use the picture of the Valkyrie. And I'm going to do a thought experiment here. Notwithstanding, it's not 100%, I'm not accounting for everything like gravitational fields, the rotation of the Earth. Goodness, can someone quash that? Jamie? No, I don't have any mods. I'm going to have to do this myself. All right. Got him. I just use one word and it just goes crazy. Okay, Valkyrie. Valkyrie. So let's say we have a nice fast airplane, and I'm just picking the picture of the Valkyrie because I think it's so cute. It's an awesome aircraft. So let's say we have a Valkyrie going that way, and let's see, paste, and a Valkyrie going this way. And then we have, let's say, a cesium beam atomic clock at the airport, or some fixed reference frame, quote unquote fixed. It's not really fixed because the Earth is rotating, but let's just imagine the Earth were rotating, okay, and it was stationary. So hypothetically, so what would be this cesium atomic clock? So there's a cesium beam atomic clock. Oh my goodness, we have here's atomic clock and paired wrist watch. It's made in Switzerland. There you go, Ben Rex. It's a 55-pound. I want me one of these. I want a very precise clock. That's too funny. Why do they have to put these blasted advertisements that I don't want? Obnoxious. So this is a $2.7 million atomic clock. $2.7 million. Okay. So I'm going to save this. Atomic clock. Atomic clock. All right, so we have an atomic clock here on the Earth station. And let's just, I don't know, maybe we'll put this kind of like at the airport. So let me see if I get a picture of a airport. So let's have a picture of a control tower somewhere. Okay, this is a nice looking control tower. Let me save. I like this picture of a control tower. I like pictures have a way of just conveying things. So this control tower has an atomic clock. And the airplanes also have atomic clocks in them. So let's say we have an atomic clock here at the control tower. And we also have like an atomic clock on the airplane. So just like the Valkyrie experiment. Now let's say hypothetically we could get them, okay, we're going to try to replicate this Valkyrie experiment earlier, except now, this is now a thought experiment. Oh, greetings, Mr. Jetty. We can use this Lorentz transformation, and I'm going to embarrass myself. It'll tell us how much the clock will slow down. And I keep getting this backward, how to apply it. So the higher the velocity here, that's going to give a transformation factor. So if this is a big number, 1 minus this will become small. The gamma will become bigger and bigger the higher your velocity is. So how much will your clock slow down? Let's see. Dilation. Okay, hyperphysics. I like this website. By the way, daylight savings time is going to expire tomorrow. So daylight savings time will expire tomorrow. So adjust your clocks. So, okay, let's go to this hyperphysics website. There's length contraction and time dilation. So let's see if we can get So I'm going to insert a value for T. Okay, say 99.999%. Oop, didn't like that. How about this? Okay. So let's look at this. So I'm going to just use 99%. So let's just say hypothetically when the airplanes are flying in different directions, and let's say they just have tremendous acceleration, 99% the speed of light. And I'm going to just capture the calculation I did This is the hyperphysics website. So let me just cut and paste just to kind of give it validity here. All right, so let me grab this so you know that I actually did this from the hyperphysics website. There, you have an official calculator there. And I'm going to give you a paradox. 99. All right, so I'm going to put this in here. So you're going to see the calculations here. So my calculator said this is going to be the clock here on Earth. So let me try to uncoil this. T. Anyone's welcome to correct me because I could totally screw this up, but TO is this clock. Did I get that? If I'm getting this in the wrong order, someone pipe in. TO is that clock. Let me just make this a little bigger. Give the weight a little higher. And it's also, ironically, this clock. Just rotate this. Now, the situation is hypothetically, we're coming from a stationary point. Again, I say hypothetically because we know the Earth is rotating and it's orbiting the sun. But when you get to 99% the speed of light, I think that kind of just washes out. And in fact, you don't need a precise atomic clock when you're getting time dilations of this magnitude here. And this is roughly 7. So, and then this clock then is ticking. Oops. TO is there. And this clock so let me make this, I like kind of green. Let's make that green and make it there. So T in terms of his clock will be 7 times faster ticking than the clocks here. Now, oops, I'm sorry. Sorry, I apologize. You couldn't see what I was doing. Here. So the clock in this airplane will tick. Okay, it accelerates. The clock in this airplane will be ticking 7 times slower than this one, or this one is ticking 7 times faster than this guy, and this guy is ticking 7 times faster than this guy. The question is then, if this guy is ticking 7 times faster than this guy, and this guy's ticking 7 times, if this airplane going to the left, flying to the left, is ticking 7 times slower than this guy, and this airplane its clock is ticking 7 times slower than this guy, it implies these two guys have a clock that are ticking at the same rate. Do you see the problem here? So I just developed this. This is ticking at, okay, that took me a while to get that far. What would happen then, and I'm going to duplicate, if we then turn this guy around and he had to accelerate so that he'll match the speed of this guy. He won't obviously intercept it. So I don't know how I can represent that. So maybe I'll copy from this position and paste. Let's see. I'm trying to represent this. I'm going to have to make him I'm trying to conceptualize this. What happens when he finally decelerates to this? Okay. So he's going to fly back to the airport and he's going to land. So his clock will then synchronize. Change the color here. Go back to green. Make the outline heavy. So if he turns around and he flies back the other direction, and when he lands, his clock will then be ticking as fast as this guy. And then if he continues on, and let me just duplicate. If he continues on, however, here, his clock will be moving at, let me copy this. It'll be moving at that rate. So presumably, I need to put a clock here. Copy the clock. I'll put the little clock here. Maybe I'll make, hi Bread of Life. Hi Bread of Life. Hi Rebecca. And let me just say hi to Rebecca. I think you're the only viewer right now. I scared them all away, Bread of Life, so even though you're greeting people, it's just you and me. I scared all the viewers off. It's just you and me right now. I scared off all the viewers. What I'm trying to point out is this seems rather paradoxical. Oops, let me undo that. That from his standpoint, so he underwent an acceleration going the other direction. I just want to show that this is showing there's an absolute reference frame, which is consistent with the ether. And this is what I have to work through. So let's assume we didn't have the history of these two airplanes, where we had the control towers. Let's say instead this is the reference point of this is the reference point here. So I'm going to make this green. This becomes green. And then we accelerate the aircraft. Okay. We make this the reference point clock. So we start here, and then we accelerate So let me just type in, start accelerating to match speed of the left moving aircraft. If we didn't have history of the motion here, if we just blindly applied the Lorentz transformation as we accelerate to the left, prediction would say this clock should be ticking very much slower than this clock, and we will confirm that that's not the case. The prediction will fail. That's what I'm trying to illustrate. So let me see here. So we start accelerating to the left. She says, this is a good show for nap time. If I don't respond, I'm asleep. Okay, hey, you know what? Don't take offense. I don't take offense. You know why? Because one time I was watching one of my own videos, it put me to sleep. One of my own lectures put me to sleep, so I take no offense. I'm glad I rest well. So accelerate aircraft on the right toward the left. Accelerate the aircraft on the right toward the left until it matches speed. Okay, so what we'll do, I know what. We'll now kind of hypothetically have a moving control tower. That's what we'll do. So I'm going to copy this, copy this. So let's hypothetically make this now the control tower. So let's say the aircraft carries a clock, and we're going to that's how I'll represent it. I'll have to think about it, but this is getting to be a better diagram now. What do we predict will happen as we accelerate this spacecraft, which is the picture of the Valkyrie bomber, but let's say now we accelerate this spacecraft to match this. I'm going to put a big question mark. If we don't have the history of the acceleration, what do we what is t? What is t0? What is the t0 tick rate? So now, let me say, I won't put t, I'll put tick rate. Is dt divided by dt is start or initial. I'll call it init. Initial being prior to acceleration. Just to get the subscripts in order here. Where's my subscript? I need a subscript. Subscript. Yeah, d init and now I need to unsubscript it. I need to unsubscript it. D init. And this would be D T Excel. That would be accelerated. Okay. My notation could be sloppy here. I have to think about, I need to get my notation correct. I have to think about it. The change in, okay, so we have absolute time. I have to think about the notation here. Okay, I have to work through the math, but that's basically the problem in a diagram. This is going to be very problematic. This is good enough to show Dr. Dennis, and we're going to have a conversation. I don't want to work through the, I don't want to get too abstract when I talk to Dr. Dennis. So if we had this clock here, and then we went through a long acceleration, the relative velocity, the velocity of this craft in reference to that, we'll say that there's a Lorentz transformation. Yeah. I think Dr. Dennis will figure it out right here, right with this here. What is the velocity being registered here? According to him, what is the t? Okay. What would be the Lorentz, the predicted Lorentz transformation of these relative velocities? This implies an absolute rest frame. I have to formulate this. I'm going to revisit this, but this is it right here. That this shows the ether exists. We actually were able to demonstrate it using the actual Lorentz transformations of special relativity. There is an absolute frame. And if we, there'll be an absolute frame. If we find out, how we can test this frame, whether, we can test whether we're close to the absolute rest. And so now I will close by saying this insight started to come to mind when I visited this website called the Conspiracy of Light website, and I'm going to show it to you. I put it in the video description. It's the Conspiracy of Light. Oh. He had actually expressed what the Conspiracy of Light is. Okay, so conspiracy of light. Let's see if I can get more info. He changed the website. A complete conspiracy is itself a law of nature. And so, oh yeah, this is great. He had some stuff. I wish he had stated what the conspiracy is. So let me see if he has it stated. Theory, paradoxes. He changed the website. I'm really upset now because he had this nicely stated. Okay. What is the conspiracy of light? There's the experimenter right there. Serious looking fellow. Man, this is upsetting because it used to be I could just click here and he would summarize what this conspiracy of light is. Okay, so the conspiracy of light, if I could find it, let's see if there's what's new. All right, he used to have I'm kind of upset. Some of the older versions actually explained what his conspiracy of light is. So I'm going to just have to go from memory. The conspiracy of light is that it appears that the speed of light is constant in all reference frames. It may not be. I think that's what he's saying. I'm not going to quite go that far, but it conspires to give us certain optical illusions. And it's possible that the speed of light could be variable. That's what he's saying. It may look constant, but it's possible the speed of light is variable. I will say that the clocks, I won't go quite that so far, although you know that's what I want to say, but we don't have hard experimental evidence yet, but the beginning is to say that relativity can't be quite right, and that's now becoming mainstream. You can say that now without being called a heretic because quantum mechanics is now taking precedence. And so Sabine Hassenfelder can say that publicly, and everyone, you're not going to be called a heretic now. It's easy. You can start making these claims. But he's saying that light conspires to make it appear that it is constant, and he's saying it's not. I'm gonna go out on a limb that I think Cahill has shown that there could be one-way speeds of light, and let me see. I don't know if he's claiming a simple answer yes or no would be good, and so the author says. A new theory emerged that hypothesized it would be actually Okay. Can we measure the one-way speed of light? So I think this is kind of what annoys me, is they could just say yes or no, and then and they could just say, he could just say yes or no, and then we would know if the speed, if we can measure different speeds of light. So can we measure the one-way speed of light? Okay, so Merritt mentions Ron Hatch, who is an acquaintance of John Sanford. And so we can go through, can we measure the one-way speed of light? I wish he could just say yes or no. In any event, this exercise seems to suggest that it should be possible to detect a measurable variable one-way speed of light between synchronized clocks if a universal rest frame for light does exist. And actually, determination of our true speed with respect to this rest frame would require the synchronizing signal to come from the same frame. Any common velocity between the synchronizing source, synchronized receivers will subtract the detectable velocity. This is reassuring conclusion since it implies the experiment is not necessarily impossible. So the short answer, yes, you can measure the one-way speed of light in principle, and Jason Lyle's wrong. That agrees with it. We can construct thought experiments that, if in principle we, how we might do this. It's difficult. Hafel-Keating was very close to this, the Hafel-Keating experiment, but they had to deal with gravitational effects and then the rotation of the Earth, etc. And the rotation of the Earth plus its orbit around the sun. But he says yes. And the Cahill interferometer, which I'll show you. One second, let me grab the heart of it. It's one version. I don't know. Cahill built so many interferometers. I had started to construct one myself. I had a laser, which is a very expensive laser, and I had a lot of the optical wires to do this, to try to carry it out. And all this is very challenging, and it would take some work for me to reconstruct, to recapitulate this interferometer. And I have some pieces that I don't know how to use anymore, which is really sad. Maybe this goes here. This is a very expensive laser. It's only a little device, and it's supposed to measure interference. The reason it is considered a better implementation than the Michelson-Morley experiment is because it uses refractive media, and Cahill went into all the reasons why refractive media could be better than a vacuum, and so did Demjanov. So anyway, the takeaway from all this would be this diagram here, which I need to improve. Because this does suggest an absolute rest frame. And if the clocks were not synchronized, if there were not an absolute rest frame, if the control tower here were actually moving through space, we should see that there would be variation between the clocks. That's the prediction. Maybe that's one way I'm going to frame it to Dr. Dennis. And I need to have a conversation with him, because this has implications that the ether is real. Because they're saying it's inconsistent with this Lorentz transformation, an ether. No, historically, this was consistent with because it was the belief in the ether that drove this derivation here, historically. Lorentz constructed it because of a derivation. Lorentz constructed it because of a derivation like this on the ether, on the assumption of the ether. So with that, I'm going to just shut this stream down. I've been talking for an hour 40 minutes. It's been a fun day. I was talking about all sorts of things. And so let me start to take everything down. And we'll just close out with my usual, the Rhapsody on a Theme of Paganini. Take care. Grace and peace to you all in the name of our Lord and Savior Jesus Christ. Glory and honor to him. Amen.